Greetings and salutations, everybody. This is Jacob. Okay, so how the heck do we go about solving this problem? I don't know where to even start, you say. Well, start from the beginning. That's always a good rule of thumb to follow, my friends. So let's start out by giving some definitions. So let's call this initial launching angle theta, and this angle here phi. So let's continue by finding the distances that the projectile and the mass sliding down the incline traverse. Let's start with the projectile. By distance, I mean the horizontal distance the projectile traverses, which is called the range of the projectile. And there's a formula for this range, which is r equals v of 0. V of 0 is the initial speed of the projectile. V naught squared times sine of 2 theta over g. So now let's find the distance that the sliding mass traverses. We'll call this distance d. So since this is a right triangle, we have cosine of phi equals r over d. So d equals r over cosine of phi, which is d equals v naught squared times sine of 2 theta over g over cosine of phi, which is d equals v naught squared times sine of 2 theta over g times cosine of phi. So now let's find the acceleration of the sliding mass. Let's turn our attention to this triangle here. Since this is a right triangle, this angle here is 90 minus phi. And since these two forces are perpendicular to each other, this angle here is phi. So sine of phi equals f over m times g, which is sine of phi equals m times a over m times g. The two m's cancel out, and we have the acceleration of the sliding mass equals g times sine of phi. Okay, so what does the problem state? It says that both masses start at the same time and get to the bottom of the inclined plane at the same time. Hence, their flight times are the same, correct? So let's find these flight times, starting from the sliding mass. So from the equations of kinematics, we know that the distance a mass traverses with acceleration a, starting from rest, zero velocity, that is equal to 1/2 times a times t squared, correct? So the flight time of the sliding mass is, we solve for t, and we get t squared equals d over 1/2 times a. And we plug in the second and the third equation in this one, and we get t squared equals v naught squared times sine of 2 theta over g times cosine of phi over 1/2 times g times sine of phi, which equals to 2 times v naught squared times sine of 2 theta over g squared times sine of phi cosine of phi. And this is t equals square root of 2 times v naught squared times sine of 2 theta over g squared times sine of phi cosine of phi. So let's now find the time of flight for the projectile. Well, there's already a formula for that, which is 2 times v naught times sine of theta over g. Since these flight times are equal, we equate them, so we get square root of 2 times v naught squared times sine of 2 theta over g squared times sine of phi cosine of phi equals 2 times v naught sine of theta over g. And we do the calculations and all the algebraic simplifications, and we end up with tangent theta equals 1 over sine of phi cosine of phi. So as you see here, we had 3 variables, but one of them canceled out, the v naught. So now we have 2 variables, theta and phi. So now we need one more equation, my friends. So let's look at our other initial condition. What does it say? The two masses reach the bottom of the inclined plane at the same speed. Now the speed of the projectile when it reaches this point will be the same as its initial speed due to the principle of conservation of energy. Makes sense? So the final speed of the projectile equals v naught. So now let's find the terminal speed of the sliding mass. So since the sliding mass starts from rest, then its terminal velocity will be u of f equals a times t, correct? Which is v of f equals g times sine of phi times square root of 2 times v naught squared times sine of 2 theta over g squared times sine of phi cosine of phi, which is v of f equals this expression here. So now we equate these two terminal velocities, and we get v naught equals v naught times square root of 2 times the square root of sine of 2 theta times the square root of tangent phi. And after we do our algebraic manipulations, we get sine of theta cosine of theta equals 1 over 4 times tangent phi. And this is our second equation. So now we just solve this system of equations. So how the heck do we go about doing that? you ask, with these trigonometric equations? Well, there are many ways to skin this cat, my friends. One such way is to divide the first equation with the second equation, and we get this expression here. And we do the calculations and all the algebraic manipulations, as we always do, and we end up with cosine of theta equals cosine of phi over 2. And using this identity here, we get sine of theta equals square root of 1 minus cosine squared of phi over 4. So we take these two results and we plug them into our first equation, and we get this expression here. And we simplify this down to 1 plus sine squared phi times 1 minus sine squared phi all over 4 times sine squared phi equals 1. We make a change of variables. We call sine squared of phi equals x. So we get 1 plus x times 1 minus x all over 4 times x equals 1. And we simplify this down to a quadratic equation. X squared plus 3x minus 1 equals 0. The roots of which are x equals square root of 13 minus 3 all over 2, and x equals minus the square root of 13 minus 3 over 2. The second solution is eliminated because sine squared of phi can't be a negative number, so our solution is a first root. And so sine squared phi equals square root of 13 minus 3 all over 2, which is phi equals arc sine of square root of 13 minus 3 all over 2, which is approximately 33.16 degrees. And we plug this value into our first equation, and we get tangent of theta equals 1 over sine of 33.16 times cosine of 33.16, which is tangent theta equals 2.183, which is theta equals arc tangent of 2.183, which is approximately 65.38 degrees. And that's your answer. 65.38 degrees. Quite an intuitive answer, if you ask me. Oh, yes. So that was quite a good physics puzzle. Wouldn't you agree? I'm glad I stumbled upon it in my puzzle of searching escapades. Problems concerning projectiles and inclined planes are very interesting, my friends. The sky's the limit. I plan on including exercises with circuits, pulleys, springs, and various other contraptions, my friends. The wonderful world of physics has no limits, as we all know. Let me know in the comments section if you found this difficult. Smash those buttons like there's no tomorrow, as always. And if you have any puzzle suggestions, then send them my way. I'm more than happy to showcase a puzzle you suggested, my friends. That's pretty much it, and I'll see you guys in the next video. Bye-bye.